Hello student, welcome to chemistry classes. Today we discuss part 2 of chapter 2 structure of atom standard 11. So we start with developments leading to the Bohr's model of atom. So we know Niels Bohr utilized this result, means that the atoms contain nucleus and electron. In nucleus, proton and neutrons are present. So from this result, Niels Bohr developed two developments. First is dual character of the electromagnetic radiation, which means that the radiation possesses both wave-like and particle-like property. So from this, one MCQ may be asked that the wave having dual nature, particle-like and wave-like. Okay, every electromagnetic radiation have dual nature, wave-like and particle-like. Second, experimental result regarding atomic spectra that we discuss later in this unit. That which experiment is performed for identification of atomic spectra. Now we discuss wave nature of electromagnetic radiation. As we know, electromagnetic radiation, which is also known as EMR. So EMR have dual character. One is wave and second one is particle. So James Maxwell performed a practical and he concludes that EMR, electromagnetic radiation, have dual nature. So according to James Maxwell, electromagnetic waves are associated with electrical and magnetic field. So remember one thing, that if we have this type of electric field, so right angle to this, we know right angle means 90 degree. So another radiation, electromagnetic magnetic radiation, are propagate on right angle to electric wave. So always electric wave and magnetic wave are right angle to each other and they are propagate on a same direction. The electrical and magnetic field components of an electromagnetic wave, these components have the same wavelength, frequency, speed and amplitude, but they vibrate in two mutually perpendicular planes. Here electric waves propagate on z direction while magnetic waves propagate on y direction. Okay, so they are always right angle to each other. Now this is very important, you have to write down this in your notebook, that properties of electromagnetic wave. The oscillating electric and magnetic field produced by oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of wave as shown in figure. Okay, so just you have to remember that electromagnetic wave, electro wave and magnetic wave always are in perpendicular to each other and moves in a same direction. Okay, second, sound waves require medium to propagate, while electromagnetic waves do not require any medium to propagate. They can move in a vacuum also. So what is our second point? So electromagnetic waves do not require any medium to propagate, to move. Okay. Next one is, it is now well established that there are many type of electromagnetic radiation which differ from one another in wavelength or frequency. Means electromagnetic we can also separate electromagnetic radiation in subparts, and they have different wavelength and frequency, and the constitution, the combination of that electromagnetic radiation are known as electromagnetic spectrum. So there are many types of electromagnetic radiation having different wavelength or frequency, and the combination of this electromagnetic radiation are known as electromagnetic spectrum. So which are this EMR, means electromagnetic radiation. So for example, radio frequency having frequency 10⁶ hertz, which is used in broadcasting. Second is microwave. The frequency of microwave radiations are 10⁻10 hertz. It is very important for MCQ and which is used for radar. Another is infrared region. The frequency of IR region is 10⁻13 hertz, which is used for heating. Second one, next one is ultraviolet region, UV region. The frequency of UV region is 10⁻16 hertz. Hertz is a unit of frequency. Okay. Second inverse. Now, ultraviolet region are found in sun radiation, and we know UV radiation are responsible for cancer, skin cancer. The next one is small portion around 10⁻15 hertz, which is known as visible light, and the things which is comes in a visible region we can see with our eyes. Okay, only visible region we can see or our eye can detect. Special instruments are required to detect non-visible radiation. Means if you want to detect UV, infrared, microwave or radio frequency, you need a specific instrument because they are non-visible. See this chart. Here frequency is given, and bottom wavelength. Okay, so gamma ray, X-ray, UV, IR, microwave, radio wave, FM and AM, and long radio wave. So these are the region of radiation. Okay, different. Here it is visible region. So see, it is visible spectrum having wavelength 400 to 750 nanometer. The region for visible light is 400 to 750 nanometer. Remember this for a MCQ. Okay, means VBR we know violet, blue, indigo, blue, green, yellow, orange and red. Okay, the wavelength of red region is highest 750, and wavelength for violet is lowest, that is 400 nanometer. Okay, now next property is different kind of unit are used to represent electromagnetic radiation. One is frequency, another one is wavelength. The The SI unit of frequency is hertz or second inverse. It is defined as number of waves that passes a given point in a 1 second. Okay, number of waves that pass a single point in a 1 second are the frequency of that light or that radiation. Wavelength should have unit length, so its unit is meter, centimeter or centimeter. In vacuum, all type of electromagnetic radiation regardless of wavelength travel at same speed. In vacuum, the velocity of all radiation are same, that is 3.0 into 10 raised to 8 meter per second, which is velocity of light. This speed of light is symbolized by C. The frequency, wavelength and velocity are related to each other by equation V is equal to C is equal to V into lambda. Lambda is wavelength, here V means mu frequency and C is velocity of light. We can say mu is equal to C by lambda, which this equation we use in numericals. Okay, so remember this equation. Now, particle nature of electromagnetic radiation. We already discussed the wave nature of EMR. Now we discuss particle nature of EMR. So Planck's performed one experiment which is well known as Planck's quantum theory, which explains us as the EMR having particle nature. So in this experiment, diffraction and interference can be explained by the wave nature of electromagnetic radiation. Here some observation which explains the wave nature of electromagnetic radiations. Okay, so first observation is the nature of emission of radiation from hot bodies. Okay, black bodies radiation means every black body are emit some radiation. Second, ejection of electron from metal surface when radiation strike it. Okay, we know any metal having nucleus and electron around it. So when you strike a radiation on surface of metal, what happen? This radiation strike to the electron and electron get removed from its orbital. Okay, which is known as photoelectric effect. Okay, after striking of radiation to the metal surface, the electron of metal surface are ejected from its atomic orbital, which is known as photoelectric effect. Next one is variation of heat capacity of solid as a function of heat. And third one is line spectra of atom with the special reference to hydrogen that we discuss later in this unit. Okay, so you have to just remember this observation. So what is Planck quantum theory? So an ideal body, so this question may be asked as write about Planck's quantum theory. So you have to start from here. An ideal body which emit or and absorb radiation of all radiation uniformly is called a black body radiation, and radiation emitted by such body is known as black body radiation. Means anything which absorbs all radiation, then they are known as black body. And if this body emit radiation, then it is known as black body radiation. We know